Welcome to this training about the basics of low consistency refining. Paper is made in the beater. You may have heard about this old saying before. In any case, you will find out where it comes from soon. I'm Frank Meltzer and I'm responsible for technical sales at Mercer Pulp Products. Refining is an essential part of my daily work since it does represent a very important link between pulp and paper. A link between Mercer and our customers. Refining enables us to influence and modify fibers in such a way that we can manufacture paper products with very diverse properties. To fully exploit the potential of refining, you require good knowledge of the theoretical relationships on the one hand, and of course, practical experience on the other. At the end of this training module, you will have an understanding of the key refining parameters and how they are interlinked. You will also know about their relevance for the fiber treatment. With this knowledge, you will be able to benchmark your refiner setup and to evaluate your mill refining system. To get there, we'll first look at the definition and importance of refining. Afterwards, we have a glance at its historical development. Then, we'll come to the heart of this training and I will explain the basic terms.
Chapter 1. Definition and Importance. In the first chapter of this training, you get to know the definition of the term refining and its significance for paper making. What is refining? Refining is a subcategory of the overarching term grinding, which originates from process engineering. In our industry, the term refining describes a process for fiber treatment which modifies the fiber structure. An important measure of the quality of a grinding process is the increase in specific surface area, which influences other processes such as drying, dissolution, or chemical reactions. Refining has a large influence on the quality of fiber-based products like paper, board, and tissue, to name the major segments. It is primarily about creating bonding areas and increasing the fiber's potential to interconnect. The refining process influences the properties of the single fibers so that as a network they meet requirements of the final product. Refining is the only process by which a paper maker can specifically influence fiber and thus paper properties such as strength, optical and surface characteristics or formation. Therefore, refining definitely plays a key role in paper making. But despite its importance, refining has been neglected over the last decades. You might ask why? Before answering this question, I want to briefly review its historical development. Chapter 2. Historical development. In Chapter 2, you learn about the historical development of refining. This involved the early development of discontinuously operating devices and the later change to continuously operating machines. Devices for the treatment of fibrous materials were developed dependent on their availability. In the early days of papermaking, the most frequently used material was rags. The main purpose of these early grinding units was to disintegrate and to cut raw materials in order to make them usable for manufacturing a decent sheet of paper. Disintegration took place in stamp mills or the collar gun, also known as a pan grinder. Later on, in the so-called Hollander beater, fibers were highly diluted in water and processing took place between the drum and the counterplate. Originally made of stone, both were gradually fitted with steel and bronze knives. As this training continues, I will use the term bars rather than knives. Hollander beaters reduce the processing time by 75% compared to stamp mills and collar gun. In those days, the beater man was the most important person in the mill. Exactly he is the link to the statement from the beginning. Paper is made in the beater. The beater man relied on his experience, optics and haptics, and simple test methods to determine if the fiber treatment for specific paper grades was sufficient. A routine procedure, for example, was a knife test, in which he checked how the fibers hung over the blade. He used it as a measure of the flexibility achieved. On the basis of the Hollander's working principle, already in the late 19th century, papermakers like Jagenberg developed key figures to describe the beating process. He introduced parameters like edge length, beating area, and beating pressure. Nowadays, these very parameters are still, though modified and extended, the basis for assessing the refining process. We will cover them later in the training. New influences on the refining process as we know it today were new and different raw materials, in particular mechanical and chemical wood fibers, changing conditions with regard to fiber treatment, more demanding quality requirements, and increasing production capacities with wider and faster paper machines. Therefore, a big step was when paper makers moved from discontinuous Hollander to a continuous production process, starting in the middle of the 19th century. With this development, there was also a change of concept from mill or beater to refiner. Initially designed as long cone, shallow angle, and single disc refiners, the dominant types are now short cone, shallow angle, and double disc refiners. In the recent past, a cylindrical design has also become established. The geometric designations refer to the shape of the respective bar holder, the so-called fillings. Common to all is the bar-to-bar principle of fiber treatment.
Let's come back to my previous comment that the industry had disregarded refining for quite some time. Which developments contributed to this situation? And why has refining attracted attention and interest of the paper makers again?
Historically, virgin fibers represented a significant share of the raw material source. The efficient operation of paper machines, the so-called runnability, depended very much on the strength of such fibers. Therefore, refining was very important during that period. The need for refining decreased for a number of reasons. Paper machine technology, for example formation as well as support and guidance of the paper web, improved significantly. Secondary fibers have become the dominant raw material source. Globally, chemical pulp accounts for only roughly 30%, of which more than half are short fibers. Another reason for the decline in refining were the high energy cost. Moreover, enzymes were considered as cheap and equivalent alternative. As a result, many paper mills no longer dealt with refining. They shut down and in many cases dismantled their refiners. Expertise was gradually lost. So why has refining become the focal point of interest again? There are a couple of reasons. The decline in consumption of graphic papers has reduced the source of high-quality secondary fiber grades. Strength or performance of the final product and not paper machine runnability has become a determining factor, suffering from the continuously decreasing quality of secondary fibers. The use of virgin fibers is on the rise again in order to compensate for both developments. Also, specialty papers with their tailor-made raw material recipes require customized refining concepts. And lastly, energy costs are not the all-important criterion anymore, and enzymes as an alternative treatment have not become established. Chapter 3. Basic terms. Now that you understand the importance of refining, in this chapter we will cover the basic terms of refining, their meaning, and how they relate to each other. Understanding these basic terms helps you utilize the full potential of refining and achieve the desired changes in the fiber structure. Since the introduction of the Hollander beater, the principle of refining, bar-to-bar treatment, has not changed. There have been interesting approaches for alternative treatment principles, but to date, none of them have prevailed on an industrial scale. Modern refiners generally work in a consistency range of about 4%. The bars treat the fibers and the grooves allow for fiber transportation through the refiner. The fibers flowing through the refiner in the grooves are captured from the leading edge of the rotor bars and then drawn into the refining gap formed by rotor and stator bars. The gap is very small, with approximately 50 to 300 micrometers, and it varies depending on the type of fiber, refiner load, and fiber conditions. Here is an example for comparison. A softwood fiber has a diameter of approximately 30 micrometers, whereas the eucalyptus fiber diameter is approximately 16 micrometers. A recent, very important finding is that the refining effects are caused by mechanical forces at the bar edges and between the bar surfaces. There are 4 different mechanical forces which are important for the fiber treatment: compression, bending, shear, and tension. Compression and bending forces contribute to fiber flexibility through internal fibrillation and delamination of the fiber walls. This means that water can penetrate into the fiber structure and promote swelling. Do you remember the knife test? This is exactly what the beta man checked up upon. Shear forces, on the other hand, promote external fibrillation. It exposes fibrils and increases the binding potential of the fibers. In addition, fines are generated by separating fibrils from the fiber wall. Lastly, tension forces stretch the fibers and help to straighten them. If these forces exceed the limit of the individual fiber strengths, the fiber breaks. Now, we have a first idea what happens to the fibers inside a refiner. The question is which effect is most desirable for a paper maker. Generally speaking, internal fibrillation from compression and bending is more desirable than producing fines and shortening fibers through shear and tension. That being said, it is important to know that all four effects usually occur at the same time. Fiber morphology plays a crucial role in this as well. However, through proper selection and application of key refining parameters, we can move the focus in one or the other direction. So let's have a look at these parameters through which a papermaker can influence and control the refining process. The most common method for quantitative characterization of refining is the net specific refining energy, SRE, which is a measure of how much power is transferred to the fiber mass. It is a quotient of the net power of the refiner and the mass flow to be treated. The net power is a difference between the total refiner power and the so-called idle or no-load power. So, what is no-load power? This is a power that is necessary to overcome mechanical friction and to pump the fiber suspension through the refiner. No noticeable changes in fiber properties should occur when the refiner is idling. As this definition is quite academically and in practice almost untestable, the no-load power should be determined at a given refining gap whose further reduction will rapidly increase the refiner power. For research purposes and laboratory trials, it is quite common to use water instead of pulp for determining no-load power. In a paper mill, measuring no-load is commonly possible and meaningful with stock only. Knowledge of no-load power and its influencing factors is important for any refiner operation. This applies both from a technological and an economic perspective. No-load power accounts for about 15 to 20% of the installed power depending on the type and size of the refiner. You always pay for it as soon as the refiner turns, no matter how you operate it. Therefore, the goal is to utilize the total power of the refiner as much as possible in order to maximize overall machine efficiency. It is also interesting and worthwhile to look at the parameters that impact no-load power and the degree to which they impact it. Those parameters are the direction of rotation, the peripheral speed, the throughput, the height of the bars, the bar angle, and the filling diameter. The direction of rotation and peripheral speed are usually fixed values, unless you do a pole change on the motor or have a variable speed drive. Both are very seldom. However, you have to be aware that no-load power increases almost with the third power of refiner speed. During operation, throughput and especially bar height influence no-load power. Wear plays an important role as well. The difference in no-load power between a new and worn filling can be as much as 30%. When changing a filling, the bar angle and filling diameter can be different. The latter in particular has an enormous impact. For example, changing from a 20 to a 22-inch plate in a disc refiner will increase your no-load power by 50%. Though entering the equation with more than the fourth power, its impact is often underestimated. Now you may ask yourself why to use larger fillings when this increases no-load power. This is a good question, which we will discuss later. If only the net specific refining energy was important for the refining process, refining could be very easy. Look at this graph. We apply the same amount of energy for the same pulp, but the result, in this case tensile strength, is different. It is obvious we need a second parameter for describing the refining process. You remember the refining effects we talked about earlier, like internal and external fibrillation. Which of those effects is more or less pronounced also depends on how energy is transferred to the fibers. To illustrate this, we can describe the specific refining energy E as the product of two factors, frequency and intensity. This means that the specific refining energy can take a constant value by being transmitted in different manners, with high intensity and low frequency, or low intensity and high frequency. Imagine you want to cut a branch with an axe. You can hit the branch twice very hard or 5 times with less force. Even if the overall applied energy is equal, you cut the branch in the first case, while in the second case you barely create a notch. Therefore, intensity is the second important parameter for describing and controlling the refining process. It is common to express this key figure using a so-called machine intensity. In other words, it is a measure of how the energy is transferred to the fiber via the bars. The most widespread intensity figure is the specific edge load SEL. It is defined as the quotient of net refiner power and the cutting edge length CEL. In simple terms, cutting edge length is the product of the number of rotor bars, the number of stator bars, the average bar length, and refiner speed. Therefore, it is a measure of the total available bar length of a filling and describes through how many bar edges and bar intersection points the refiner power is transferred to the fibers. The important question now is, how does intensity influence the refining result? If refining is carried out with low intensity, the effect of internal fibrillation is more pronounced, resulting in better strength properties. In contrast, at high intensity, fibers are subject to more external fibrillation with increased fines, fiber shortening, and lower strengths as a result. When it comes to drainage resistance, expressed as shoppericler or freeness, applying a lower intensity will require more specific refining energy. While increasing the intensity makes the process more efficient, it happens at the expense of strength characteristics. In order to influence the intensity at a given refiner setup, the only option is to adjust the refiner power. Assuming the specific refining energy that needs to be transferred is defined and intensity appears to be too high, you have two options. You can either split the amount of specific energy between two refiners operated either in series or in parallel, or if a second refiner is not available, you can install a filling with a higher cutting edge length. This you can achieve by selecting a design with a higher bar density. You can also stick to your standard filling design and use a larger diameter plate. This consideration brings us full circle as it takes us back to the question why someone would use a larger filling, though this will increase no-load power. The simple answer is, in order to lower intensity, increase internal fibrillation, and promote strength, but at the expense of a lower overall refiner efficiency.
During the last 15 minutes, you've acquired theoretical knowledge which will enable you to review your refiner or refiner system. As a start, you can check if the basic settings are reasonable. As mentioned before, fiber morphology plays a major role in selecting the right refining parameter. In view of the fact that, in general, not a single furnish but different types of fibers are employed for making paper products, fiber morphology represents another important topic to look into and to understand. If you feel you need support with this, I recommend to ask for third-party help or expertise. We at Mercer offer tools and options for technological support. At our standard mill in Germany, we established a fiber center which is dedicated to mill refining studies. We are fully equipped for pulp and paper testing and other analytical work. The core equipment of our fiber center is a completely automated laboratory refiner composed of pulper, monopump, the refiner itself, sampling station, and controlling unit. It is designed to simulate the mill refining process based on specific refining energy and specific edge load. We can use disc or conical fillings and have the flexibility to adjust for industrial applications. Please feel free to contact me in case you have questions regarding the content of this training or if you want to discuss specifics of your mill refining system. My email address is frank.meltzer@mercerint.com. Thank you for joining us today. I'm looking forward to further discussing refining with you. It is definitely worth it.